In this video here, we're going to talk a little bit about the idea of inductance and then items, electrical components called inductors that sort of come from this property. So what we've sort of seen in the past videos here is that we get a magnetic field more or less from a current. We've seen this time and time again for the wire, for instance, like that, the straight wire, the magnetic field is mu naught I over 2 pi r. And all the magnetic systems that we looked at, like the solenoid, the magnetic field is mu naught times the number of turns divided by the length times I. And even for the charge, not the charge ring, but the ring of current in there, if you look at that for me carefully, it's sort of a big messy one, but B is also proportional to I. So we've seen just several systems here where the magnetic field is clearly sourced or comes from a current. Both of these, all of these equations here have a current that gives a magnetic field, a current that gives a magnetic field, and in that ring of current, it was a charge that gives a magnetic field. We've seen that 3 times now, and the list goes on and on. So the magnetic fields come from current. But what we found out when we were talking about Faraday's law is that it seemed like suddenly it wasn't so much the magnetic field, but the magnetic flux was important. So then it seems like, is there a relationship then between magnetic flux and current? Because we know that current drives magnetic field, or the current is the source of the magnetic field, and we know that flux here is definitely related to the magnetic field. Magnetic flux is definitely related to the magnetic field because it's just magnetic field times the area times the cosine of the angle between them. So we know this relation holds here. So if current makes magnetic field and flux depends on magnetic field, is there a more direct relation between current and magnetic flux? That's the issue, and there is, and it's called inductance. So we can sort of go at a relation like this. This is sort of what we just discussed here about how the current gives rise to magnetic field. But it turns out then that there is a direct link between magnetic flux and current, as we mentioned here, almost skipping the magnetic field. If you bring all this together then it's like this. The magnetic flux is something called L times I, where this parameter L here is called the inductance of the system. Now inductance is kind of a tough property to describe and get a handle of here. It's probably going to take a while on that here. But it is a property that gets categorized with us, things that you know about by now. Like another electrical property of devices here is resistance, R. And you remember that resistance here is a way of impeding or slowing down charge in the circuit. Of course, another electrical property devices have are capacitance, the ability to store charge, C. So we have resistors which slow down charge and capacitors which store charge, and the other properties of resistance and capacitance. So we have these properties. Well, it turns out then that where you categorize inductance is just added to this list here. So maybe you learn about resistors first and capacitors second. Now here we are, number 3, learning about inductance. So these are the 3 core electronic properties that generally all devices have. They have some resistance, some capacitance, and some inductance. And inductance comes to mind here, or is defined rather, as that proportionality constant between the magnetic flux, which has to do with sort of the capturing the flow of magnetic field lines, and current, which fundamentally gives rise to magnetic fields, but we know magnetic fields and flux are related. So this is sort of where inductance is defined. So what are some things to think about then when you hear the word inductance or L like this? Well, I think the best way to think about inductance for now, particularly this level here, is think of an electrical system, or I shouldn't say system, but maybe component. Or system would be fine, I guess either one, electrical component, and think lots of wire and loops. That's really the best way to think about it. So what sort of device can you think about that has lots of wires and loops in it? Well, things like motors. So let's have a lot of windings in the motors, as we did a little video on motors a while back. A lot of those windings there to increase that force to get the motor spinning in there. And you have things like coils. Automobiles used to have old coils that got high voltage for spark plugs and that sort of thing, coils in there like that. Things like pumps, swimming pool pumps or water pumps, because those are really just motors in there. These things tend to have a large inductance too. And just anything you can think of with lots of wire in them. Transformers are another case here. Transformers are these things that can change, step up and step down voltages and currents, and they have a lot of metal and wire wrapped around them and that sort of thing. So all of these things are sort of thought of as having the big things that have inductance. So you wouldn't think of a little capacitor really as having similar properties as a motor, or a resistor having the same properties as a pump, although motors and pumps do have the property called resistance. But because of all their wire and loops that these things typically have, they're going to have a large amount of inductance. And so these things have this property of inductance that would have to sort of be grappled with if they were going to be used in some sort of circuit or anything like that. So that's about all we'll say about the property of inductance at this point. But we can say one more thing after we get done with the next sort of portion of this video here where we talk about inductors. But just remember the three electrical properties here. Resistance slows the flow, capacitance stores charge, and inductance is, well, we'll see what it is. But I guess we'll just sort of say right now that inductance here, what this is going to be, it's going to be a resistance to changing current. That's what we'll see inductance will be. But let's get on. Let's talk about inductors and see what inductors are. Okay. So what an inductor is actually a pretty simple device to build. All you have to do is take a piece of wire like this. Just a straight piece of wire. Just make it into a bunch of loops. Just so take that wire and just do whatever you have to do to it to make it into a bunch of loops like this. Same piece of wire, but all you're doing is taking that midsection over there and curling it up. And I have a couple leads here you can use to feed it into the rest of your circuit. So what you think of now is like what's going to happen with this thing when a current enters the system here. So here comes a current. And the current can come from anywhere. You can connect it like to a battery like this or something, whatever the case may be, but you're just suddenly going to inject this straight piece of wire, which has now been curled into a bunch of loops, into the system. What happens? Well, what's going to happen here is we'll try to be a little careful with the way we do this thing here, is that the current's going to try to start traveling through this system here. It will travel through the system because it's a wire after all. And what will happen then, of course, is a magnetic field will build up in here. And let's see if the current's sort of going up this loop. Looks like it's going to be coming down in the front right here. If I use the right-hand rule and put my thumb in the direction of this front loop right here, this front piece of wire, and curl into the solenoid, looks like what will happen is that a magnetic field would like to build up inside here. In other words, in this inner core of this coil that you made by wrapping a wire, that's where a magnetic field is going to build up. But remember that magnetic field buildup can't just happen quickly like that. Why? Because remember what the inductor looked like at the beginning here, right after we wrapped it, before we turn on the current. The inductor was sort of sitting here like this. And we just hypothesized then what would happen if we started to inject current into the system here. Like that. So a nice empty inductor. And now hopefully you know from Faraday's law and so on and so forth that it's difficult to go from a no magnetic field scenario to a strong magnetic field scenario. It's difficult to do that. Why? Because there's always this EMF which gets induced in the other direction. This is Faraday's law, says we really like to oppose, that's what the minus sign means, oppose changes in magnetic flux. That's what Faraday's law tells us. That's the epitome of the rule there. And we also have its sort of close cousin, which we call Lenz's law. And what Lenz's law tells us is that if you inject current in the system, a magnetic field will be induced to try to oppose that change. And so these two laws tell you here that it's sort of, there's always a reaction when you try to change the magnetic field environment. You get a voltage induced in the opposite direction, and Lenz's law has these words about a buildup of some field to oppose the change in magnetic field. So you go back to your good old inductor here and go, okay, you went from this inductor that had no magnetic field, you're trying to inject current into it, and you know that when current gets injected, a magnetic field is going to build up. But you want to oppose changes in magnetic field. That's what these two laws tell you here. So what this system is going to do here, just this simple coil of wire here, is it'll say, okay, you want to build up a magnetic field like that, and you'll likely eventually win, and usually you do win because the battery here is sort of like an infinite power supply. You just keep pumping the current in. But as you go from the transition of no magnetic field to strong magnetic field, there's going to be an induced magnetic field which is going to point this way, and an induced current which is going to point this way as well. So B induced and I induced. Now I'm just guessing on those directions, but I know if the green injected current generates the blue rightwards magnetic field, then a purple induced magnetic field the other way must be driven by current in the other direction. That's just sort of some common sense in there. So this is exactly what happens if you try to inject current into an inductor or a coil of wire. So what we built here, this is an inductor. Just this coil right here is an inductor that we built here, and we're trying to inject current into it. And so what you get here, at least initially right here, is you try to inject the current in, and you have this induced current going the other way. Sort of your net current in the system is going to be zero. You're saying, well, wait a minute now. I thought I'm trying to inject current in the device, and you are. You are trying to put current in there. But in that initial stage, when you try to put this current in this inductor, which has no magnetic field in it, this induced field is going to be quite strong. This induced current is going to be quite strong to the point where your net current is going to be zero. or close to it. And this is exactly what we mean by the property of inductance. The coils, the motors, the pumps, these things with a lot of coil and metal like that, is that the property of inductance here is all about resisting changes in current. That's what the property of inductance is all about. And you can categorize that in your mind, sort of on your list of electrical devices, with resistance, which is sort of impedes current. So it didn't say anything about changing current the way inductors are. It just impedes any current that you send it near its way. And capacitance is about storing charge. The word current doesn't even enter that fundamental capacitance sort of vernacular there, but that's what that's all about. So you have your three properties here. Inductance is about resisting changes in current here. Resistance is about impeding current, and capacitance is about storing charge. So again, back on target about resisting changes in current. When you have this system here initially with no magnetic field, this is a huge change in current which you're trying to inflict on it. You're trying to go from sort of zero current like this to some maximal current, perhaps predicted by Ohm's law, that this battery is trying to pump through this otherwise resistive system that it has here. That's a big change in current. And the bigger the change in current that you try to force this inductor to undergo, the more it's going to resist it. So the law then for inductors is that looks something like this here. The voltage across an inductor is always minus its inductance, because remember, there's always this opposing effect in here. If you try and inject a current to the right, the induced current is going to be to the left. There's always this opposing current. That's what the minus sign means in there. Minus L times the derivative of current with respect to time, di dt. So this is the voltage across an inductor. And we like to look at it just sort of empirically like this. Now, if you're curious where it comes from, it does come from Faraday's law. Faraday's law says that the reverse EMF here, or induced EMF, comes from the derivative of the flux with respect to time. But what you have here in the sort of the solenoid or the inductor like this is, you know that the magnetic field is mu naught times N over L times I. Now, don't get L confused here with inductors. I'll just sort of write it as a script L, indicating the length of the solenoid or the inductor in there. But if you put all this together here, knowing that that flux is equal to B times the area and so on and so forth, put this into there and put it all together, you'll eventually, and put it into Faraday's law here and take that time derivative, you'll eventually see that everything just boils down to what was the change in current, because even in the equation for the solenoid here, this current here is the key driving term, so a dB dt is going to have a di dt if it's going to be non-zero. We don't expect a time rate of change of the number of turns or the length of the thing, unless you're just doing some sort of bizarre problem. So you do have a key inductor equation like this, and this can very much be categorized again on your list of electrical devices, like the voltage across the capacitor is Q over C. You have that, and the voltage across the resistor here, that's just given by Ohm's law, IR. So you see you have these three equations here, all of them sort of tell you something about how your devices behave here. So this is one for your capacitor here, and this is one for your resistor here. So you have these equations for all of them. So we'll just sort of leave it at that, but we'll notice that because this video is about the inductors here, we'll just highlight this one and just a few more parting terms here about the voltage across the inductor. Notice the property of inductance just sits in there. How much inductance do we have? Just like the property of capacitance sits in this one, and the property of resistance sits in this one. The properties are all in there, but then the physical quantities it depends on here, the capacitor depends on how much charge is stored, the resistor depends on how much current you're trying to send through it, and the inductor sits in here and goes, well, it has its inductance, and the key term here is how quickly are you trying to change the current through the system, the di dt, the change in current with respect to time. This is very large, like you're trying to go from zero to maximum in a very short time, maybe a switch closure, you can get a very large induced voltage across the inductor like that. But if you're able to sort of even out the di dt or make it a little bit smaller, you get a smaller voltage in there. And so that's really where inductors are used. Uses of inductors here are to smoothen changes in current, or to sort of resist them. So you can dissect either way you want, but that's where you find inductors being used in electrical circuits, sort of as filters to smoothen signals and get rid of abrupt changes in current, because they put a large voltage out there when you get a change in current. So there's inductors and inductance for you.